Good evening, guys. Am I audible?
Yes, sir.
We'll get started.
Sir, sir, is meter bridge is bad for the portion, sir?
Which one?
Meter bridge.
Meter bridge is not there. I told no.
Yes, sir. But in school, they are telling like it's there, sir. That's why I asked.
As per syllabus, it is deleted. Okay.
Okay, sir.
But they would have told it is important because you have experiment based on it.
Oh, fine, sir.
So that is why they would have told it is important. But it's better you can learn it. I also taught you. We did problems also.
Sure.
It's easy only. Yeah. Shall we get started? I hope you're able to see my presentation. Right. So yesterday we started with the concept of refraction of light. So when you talk about refraction of light, it basically means light traveling from one medium to another starts bending, right? So when it has to bend, light travels from one medium to another, like it travels from rarer to denser or denser to rarer, based on which there is a parameter called refractive index that keeps changing, right? So how do you define this refractive index as? It is defined as the ratio of speed of light in vacuum to the speed of light in a given medium. That is for absolute, and for relative, it is speed of light in one medium with respect to the speed of the light in the other medium. Is there any doubt till this point? Shall I proceed?
Yes, sir.
Okay. So write down next heading as laws of refraction. So here also you have two laws. What are they? Incident ray, refracted ray, and the normal all lie in the same plane. And secondly, ratio of sine of angle of incidence to the sine of angle of refraction is always a constant, and that constant is named as refractive index, right? So make a note of these 2 points. Let me know once you're done. Okay. So when you take a boundary like this, the ray which is incident is called as the incident ray. So at the point of incidence, if you draw a normal, then this angle is called as angle of incidence. This would be the actual path. And when light travels from one medium to another, it starts bending either towards the normal or away from the normal. For instance, if I say it is bending towards the normal, let me call this angle as R. Then according to the above statement, sin I by sin R is equal to mu. And this law is called as Snell's law. Are you able to understand? Okay. Now see. Suppose this is a medium of refractive index mu1. This is another medium of refractive index mu2. Let's say light is incident from first medium to another. Then sin I by sin R is given as mu2 divided by mu1. Okay. So sin I and sin R are inversely proportional to the refractive indices of the respective medium. So the best way to write it is refractive index of a given medium mu1 into sine of the angle in that medium sin I is equal to refractive index of the second medium, that is mu2, into sine of the angle in that medium, that is sin R. Okay. So having this point in mind, tell me what happens when light travels from rarer to denser medium. When light travels from rarer to denser medium, what happens?
It bends towards the normal.
So light starts bending towards the normal. But why is it even happening? So for that, if you see, if you take a light ray like this, at the point, if I draw a normal, this is going to be the angle of incidence. So if this is the actual path, observe, this is mu1, mu2, and this is rarer and this is denser. So what is the relation between mu1 and mu2 for rarer and denser medium? Mu1 is less than mu2, right? So if I write the expression mu1 into sin I is equal to mu2 into sin R, observe, sin I by sin R will be equal to mu2 divided by mu1, right? So from this expression, I can say mu2 by mu1 is less than 1. So here mu2 by mu1 is less than 1, which implies sin I is less than sin R, or I can also conclude that I is less than R. When that is the scenario, then this angle will also be I, and the refracted ray should take such a path that it is always less than I. That is the reason why it starts bending towards the normal.
Sir, if mu2 is greater than mu1, then mu2 by mu1 is greater than 1 only, sir.
Oh, I made a mistake. Huh? Yeah, sorry. So mu2 by mu1 should be greater than 1. Actually, the diagram I drew is correct only, but the logic is reversed. So it should be greater than 1, which implies sin I is greater than sin R, or it also implies I is greater than R. So I should be greater than R. Okay. So if you do the reverse analysis, that is when light travels from denser to rarer, what should happen? It will bend away from the normal. So the concept is very simple, okay? When we say light is bending towards the normal, okay, when we say light is bending towards the normal, it always takes a clockwise turn. So clockwise means towards. Whereas if the same light ray is bending away from the normal, means from its actual path, it will take an anti-clockwise turn. So this is what we call it as moving away from the normal. Okay. Now, having these points in mind, let's see the applications of refraction. So, next heading we are going to discuss is applications of refraction, in which the first application we are going to see is light through a rectangular glass slab. Okay. So when light is passed through a rectangular glass slab, let's say it is incident here, then this will be the angle of incidence. So light would have traveled in this path had the boundary not existed. So if this is mu1, if this is mu2, then outside medium is again mu1. So when light travels from, let's say this is rarer, this is denser, and this is rarer again, because you're talking about a glass slab, and outside medium is generally air because we perform the experiment in a lab, right? So when light travels from rarer to denser medium, it starts bending towards the normal. So when it starts bending towards the normal, at the second point of incidence, what we can say is it makes an angle. For example, if you see this angle is R, then this angle will also be R because they are alternate interior angles. Now the light is traveling from denser to rarer medium. So denser to rarer medium means it starts moving away from the normal. Now, this will be the incident ray, this will be the refracted ray, and this will be the emergent ray. If you observe, emergent ray and incident ray, we have to see what is the relation between them. For that, we will apply Snell's law at point 1. When you apply Snell's law at point 1, you have mu1 into sin I is equal to mu2 into sin R. Let me call this as equation number 1. Similarly, if I apply Snell's law at point 2, then it becomes mu2 into sin R is equal to mu1 into sin E. Let this be equation number 2. So from 1 and 2, the important point that we are able to understand is mu1 sin I is equal to mu1 times sin E. Mu1 and mu1 will get cancelled, which implies sin I is equal to sin E. So when sin I is equal to sin E, that clearly implies that I is equal to E, or the angle of incidence is equal to angle of emergence. Is that clear? Means the extended incident ray will be parallel to the emergent ray. Make a note of this point.
Sir? Sir?
Tell me.
Sir, at any situation, will the incident ray coincide with the emergent ray? Extended incident ray.
It cannot happen. It cannot. Because the light has taken a bend. Had it not taken, then it would have happened.
Okay, sir.
Let me know once you're done copying it. Shall I proceed?
Yes.
So if you observe, we told that the incident ray and emergent ray are parallel, right? Means there is a small shift in the incident ray by the time it comes out as emergent ray. Then this shift is called delta X and it is named as lateral displacement. Okay. So this delta X is called as lateral displacement, and I'll redraw the diagram again. Observe. Now what we are going to do is we are going to calculate the lateral displacement for in glass slab. So if I take this ray, this is I, R E. Okay. Now I need to find this displacement. A, B, C. Okay. So I'll extend it from here. Let me call this point as D. Now remember, wherever you talk about refraction, then the laws of refraction has to be applied. So in one of the laws of refraction, if you observe, you have sin I and sin R. Means you have sin, which is a trigonometric function, which demands a right angled triangle. Okay. Whereas, on the other hand, what you need to do is, for distances, find the right angle triangles and apply Snell's law. Okay. So what I'm trying to say is, if I take the thickness of the glass slab, for instance, to be T, then if I take the right angle triangle ADB, the thickness is T, this is R, then cos R is how much? T divided by AB. Okay. If this angle is I, then this angle will also be I, then this will be I minus R. So when you take the other right angle triangle, which is ACB, angle A is I minus R and angle CB is delta X. So if you observe, when you write sine of I minus R, you can write it as delta X divided by AB. Let this be 1 and let this be equation number 2. Copy it to this step. Let me know once you're done. Let me know once you're done. Done? So from 2, I can say sine of I minus r is equal to delta x by AB. So sine of I minus r is sin I cos r minus cos I sin r, the whole divided by, if I write cos r here, then it will become delta x divided by AB divided by cos r from 1 is t divided by AB. AB and AB will get cancelled, which implies delta x is equal to t into sin I minus cos I tan r. Okay. So delta x is this value. So delta x will be equal to, okay. Now what I can do is, if I apply Snell's law, I get mu1 into sin I is equal to mu2 into sin r, which implies sin r is equal to mu1 divided by mu2 into sin I. But remember, in this context, mu1 is 1 because outside is air medium. And if I take mu2 is equal to mu, for instance, then that will imply sin r is equal to 1 divided by mu into sin I. So when you take the right angle triangle, right, if this angle is r, then this will be sin I, this will be mu, and the base will be root of mu square minus sin square. So what will tan r be equal to? Tan r will be equal to sin I divided by root of mu square minus sin square I. So let me call this as 3 and this as 4. So use 4 in 3, then you will have delta x is equal to t. If you observe, sin I is there here, and here also you have a sin I. So t sin I will be common into 1 minus 1 cos I divided by root of mu square minus sin square I will be the required answer.
Sir, how did you take the sin I common outside?
Because here also you have sin I. In tan r also you have sin I. You put, when you substitute in tan r, you get sin I.
Okay, sir.
Let me know once you're done. Done? Okay. The next application that we are going to see is real and apparent depth. So when you have a boundary like this, let's say there is a denser medium in which there is a luminous object which is placed. Now, let's say the object is placed at a depth h. So depth is when you measure the distance from the surface. So this is called as real depth. Okay. Suppose your eye is here. Okay. Now, you're trying to focus and observe how the object is looking to you. So if I take one of the rays to be incident at an angle 0 degrees, then it travels without any deviation. So it travels at the same 0 degrees. Whereas if I consider another ray, let's say at an angle I, then since it travels from denser to rarer, it starts bending away from the normal, and this angle will be R. Right? So the first refracted ray and the second refracted ray can never meet. If that is the case, then we need to extend the second refracted ray in the backward direction for us to get the virtual location of it. So if I take this point to be I, so if this angle is R, then this angle will also be R. So if this angle is I, then this angle will also be I. Because R and R are corresponding angles, I and I are alternate interior angles. So if I take the refractive index of denser medium as mu and the refractive index of rarer as 1, then I will have mu into sin I is equal to 1 into sin R. So let this be equation number 1. Okay. So here an important note to be made is for the eye to locate the image of object O, angle I and angle R are supposed to be very small because the size of pupil is very small. Only then these two rays will be closer to each other. Right? When they are closer to each other, then what I can say is sin I can be approximated to tan I can be approximated to I, and sin R can be approximated to tan R can be approximated to R. So make a note of this point. Okay. So when that is the case, I can use 2 in 1. When I do that, I get mu into tan I is equal to is equal to 1 into tan R. So let me call this as equation number 3. Now, if you observe, what is tan I from the diagram? Tan I is, if I take this point as A, it is AO divided by AP. Similarly, tan R will be equal to AI divided by AP. So if I take these two values and substitute it, then I'll have mu into tan I, this AO divided by AP is equal to 1 into tan R is also,
Sir, can you show the diagram 1 minute?
yeah, I'll show it. So I wrote it in the reverse, I think.
Yes, sir.
So it is AP divided by AO, and here it will be AP divided by AI. So mu into AP divided by AO is equal to 1 into AP divided by AI. Both will get cancelled, which implies mu divided by H is equal to 1 divided by AI, or AI is equal to H divided by mu, where this AI is what is called as apparent depth. So if you observe, apparent depth is equal to real depth divided by mu, which is a very, very important expression that you need to remember. Okay. Similarly, what is the shift that has taken place? Shift is OI. OI can be written as AO minus AI. AO is H, AI is H by mu. So H into 1 minus 1 by mu is going to be the required shift that has taken place. I guess clear. Yep. So this is all about the concept of apparent depth and real depth. Okay. So what are all the concepts that we discussed today? One is we saw the laws of refraction. Then what happens when light travels from rarer to denser medium? Then we saw two applications of refraction, out of which one is called as the refraction through glass slab, and the second is lateral displacement in a glass slab, actually three. And we saw real and apparent. So we have seen enough number of derivations. And the next topic that we are supposed to see is called total internal reflection, for which I'll start dealing with next class. Apart from that, any other doubt from today's class?
No doubt.
Okay. Then we'll wind up.
Thank you, sir.
Sir,
Thank you, sir.
Yeah, tell me.
sir, the diagram I didn't understand, I told.
Which one? This one. Huh?
No, sir, the one I sent you.
So that will take time. That's what I told. I'll explain in person. When you come to class, I'll explain.
Okay, sir.